All right, welcome everybody. Happy Friday. Welcome to what I think is the seminar marking the midpoint of the fall 2025 season of the Princeton Robotics Seminar. It's my pleasure to introduce our speaker for today, Professor Hsieh, who is an associate professor in the mechanical engineering and applied mechanics department.
Yes, that's right.
At the University of Pennsylvania, where she also directs the GRASP lab, which I think needs little introduction in this crowd. A couple of notes about Annie. She actually visited us at Princeton last spring, so it's wonderful to have her back here. And she's really someone who intersects really wonderfully with a lot of the faculty we have at Princeton thinking about robotics. Her work spans multi-agent systems, control theory. She's done some cool work on safety and using control barrier functions for exploration. She's done some really fun work in marine environment with swarms of robots. So it's really great to have a single human being who embodies a lot of the really fun themes that are exciting in robotics and in particular exciting to a lot of us here. Of course, I'm not the only one to think that Annie's work is cool, and she's got a lot of prestigious awards that speak to that, and I'll just highlight the NSF Career Award and the ONR Young Investigator Award. So it's really wonderful. I need to have you back. Thanks for stopping by again, and we're very excited for your talk. Take it away.
Thank you, Hsieh. Yeah, I'm already. So thank you so much. So I'm deputy director. So CJ Taylor is director. So, but that's fine. But because I am deputy director, I have to, do the following. So I have to sort of give you the overview about GRASP. So we've been established since 1979. The interesting thing about this is that was around the same time the Robotics Institute was established. These days, we're right around 27 primary faculty, and we draw them from mechanical engineering and applied mechanics, electrical and systems engineering, and computer information sciences. GRASP also administers the robotics master's in engineering degree at the University of Pennsylvania. So that's kind of my primary duties there as deputy director. And right now, we're up to 143 PhD students. This, of course, is spread out across the primary faculty. Robo has really gotten very big. There's 298 students based on our last count. And research staff, so this includes postdocs, machinists and sort of design people that helps us do the research. And if you have not been to Philadelphia and have not had the opportunity to come for a visit, I encourage you guys to reach out, and we're happy to host you. Of course, we're big. The way that I like to talk about this, especially to students, is think about any robot. This robot can be measured in terms of nanometers, or in terms of tens of meters. The GRASP faculty sort of covers that entire range depending on the size of your robot. And then it doesn't matter if your robot swims, if your robot flies, if it walks, if it drives. There's someone there that will also have expertise in those areas. And so in this regards, we are really kind of the we do cover a lot of the different areas of robotics. Okay, so that's now my prerequisite sort of 2 slides. But let's get into some of the work that my group does. So this is my group. We've just, I had actually graduated about 4 students within the last couple of months. So today the work is going to be primarily sort of some of Alice's work, some of Arjun's work, and then Kongyao which is now back in Singapore, and then some of Peon's work. But none of this is possible without my wonderful group. And then I always, tell the audience, you reserve the hardest questions to them. And I will be happy to take the easy ones. Okay, so what do we want our robots to do, right? So there's plenty of these. We want them to drive us, right, to our desired locations. We want them to be able to explore unknown planets. We want them to cook a meal for us in our kitchens, right? But, right, regardless of what they're doing, this is their task, right? They have to have an understanding of their environment. And usually, right, this sort of sense of sometimes in the case of the self-driving car, the map of the environment is kind of given to you, right? So that's given to the robot. Sometimes in the case of your Mars rover, you're going out and you have to build this map of this environment. And of course, depending on the task, sometimes you have a mix of both. You have some notion of the environment, but you don't know the full details, right? So here's my purpose robot. So this robot's purpose is to serve butter. That's right. So those of you younger folks, I have a young kid, so my adult cultural references are going to be super outdated. So feel free to ask me questions. But in most of the cases, right, this is the part of they're in their environment. I'm going to ask my robot to go get butter. It's going to have to go figure out how to navigate through the kitchen and find the butter. And then through this process, it's going to build a map, right? And then once it sort of builds this map, it's going to bring the butter back to me, okay? So this is your classic simultaneous localization and mapping problem, also called SLAM, right? So the idea here is that, it's kind of this coupled process, okay? As you're going out, right, you collect information about the map. And when you come back, right, and sort of realize that, you've seen this place before, this is an opportunity for you to improve your estimates of your state, so your estimate of where you are. But because you have this ability to get better measurements of where you are, you now have this ability to build even better maps. And so this process is kind of, this beneficial cycle, right? State-of-the-art SLAM is amazing, and I'm sure a lot of you guys have seen, right, a lot of examples. I like to pick on this one because this is an example from GRASP. So the Miller family farm is actually a former student, Ian Miller's. This was during the pandemic, so everybody went home, but they still had to do their research. And so in collaboration with Anthony and Callie, this is UpSLAM, and so you are able to, deploy your sensors, and this uses the union of panoramas in order to build your maps, okay? And so what's really cool is if you look at some of the finer features, you can see all the individual fence posts, right? Those are coming out nice, clean, and sharp, okay? So state-of-the-art SLAM is really amazing because, right, fundamental to these algorithms, there's this assumption that the features that I can detect, right, I can actually do correspondence, right? I can do matching, and that the matching, right, comes out correct. The features, and part of the reason why I can do this is because most of the features that I'm kind of sort of hanging on to is the fact that they're static. And there's a notion of consistency in terms of context, right? I am not going to see certain things, right? I don't expect to see a fish swimming in front of me if I'm walking down the hallway, right, of this beautiful building. So this is Hurricane Ida. This is Philadelphia. By the way, these are light posts, okay, that you're seeing. This is how high up the river. Normally, there's like a pedestrian jog. So a lot of people go jogging along the river. That is all underwater, basically, okay? So this is kind of this notion of, SLAM doesn't quite, right? This is kind of a perfect example of like none of those things, right, sort of holding very nicely. You take this into a slightly different environment, okay? And so the question is, okay, so then what are your static features in this case? So yes, there's stuff at the bottom of the ocean. If they're living things, they do change, right? They change over time. There's currents, the sand gets moved around. And then if you're sort of operating in the open ocean, actually this is lighten up, so there's actually light in this, but most of the time it's pretty dark, okay? And so the question is, you know, what happens, right? And so this is kind of where we started when I first got into this type of problems. So somehow okay, so this is Gulf of Mexico, okay? And if you look, this is basically the currents in the Gulf of Mexico. This is over the course of about a month or so. And what you're seeing is, if you look at this, even just as with our human eyes, we were seeing a lot of structure, right? This is the Gulf Stream right here. And then if you look carefully, eventually an eddy, so we don't have the full data set, but eventually the eddy does break off. And this is a very well-known eddy effect, okay? And this is Monterey Bay, okay? And so as terrestrial beings, right, we don't think about, right, this environment as having a lot of structure. But if you look at this from a dynamical systems lens, right, there actually is a lot of structure. And this is the surface currents in Monterey Bay. These are what we call the finite time Lyapunov exponents. And so the idea here is that if I know how to sort of tease these things out, right, so I can find these structures. So what are these things? These are called Lagrangian coherent structures, okay? They are basically, they are used to characterize transport, so how things get moved, right, by the water. It could be the individual water particles. But the idea here is that the way you find them is you have to compute what these things called finite time Lyapunov exponents. And what they measure is if you plop a whole bunch of like little things down in a particular patch of the water, how fast do those little things kind of spread apart, okay? How fast do they disperse? And so places where they disperse quickly, right, those are the places where you're seeing those red lines. So one thing too, right, that I like to make the claim is like this is an example of a structure. These are coherent because they actually persist, okay? And so this is potentially something that we can use, right, that the robots themselves can ping off of where we're thinking about building a map for these types of environments. But they're actually really important for other reasons, right? So this animation on your left-hand side, what you're seeing is you're seeing white particles and black particles, and they're being seated on opposite sides of one of these structures, okay? The structures are those sort of red lines. And what you're seeing is the fact that over time, the white particles and the black particles don't mix. So what this means is that these structures are really kind of delineating your flow field into dynamically distinct regions, okay? Another thing that was shown is that if you actually think about doing optimal trajectory generation, right, if you pose that optimal trajectory generation problem by taking the background flow into account, then time and energy minimizing paths tend to chase along your coherent structure boundaries, okay? So this actually are kind of regions where you experience high, right, flow rates. This is a simulation, so I kind of simulated. There's a little sort of place where I'm kind of outputting these black particles. And if you look at how the black particles, right, relate to those red boundaries, what you're seeing is the fact that knowing where these boundaries are actually gives you a pretty nice sense of how the particles are going to disperse, okay? So they actually tell you a lot about where things are going to go. Now, the downside, of course, is that these are global structures. So the way I find them is I have to have the entire flow field, and then I have to do computation on that flow field, okay? So it's expensive computationally. And the fact that most of the time, depending on the environment, the data is going to be very low spatial temporal resolution, okay? Just to give you a sense, most common ocean data, right, things come in at hourly intervals, right? And Monterey Bay is actually pretty nicely instrumented, but in regions where you're not well instrumented, the spatial data points can be sort of half a degree apart or anywhere, this is in terms of hundreds of kilometers apart, okay? But the claim is that, however, if I can think about these structures, right, from a robotics perspective, right, this is kind of similar to this idea of how, when we were, so I can remember when we were, dealing with raw point clouds, right? And then, or camera pixels, and then how we, our mapping techniques got better. And so now we can do features, and then from features, we can then go on, and now we can do things like YOLO, right? And do object segmentation and scene understanding, okay? But the claim is that these kinds of structures is now the thing, right, is going to be like our equivalent thing, right, in this new environment. And so this is some of the old work that we've done. I don't think this one is going to play, but this is a coherent structure. This is a really well-studied one off the coast of Santa Barbara, California. And so what we did was we kind of developed algorithms that said, look, if I have an initial estimate of where these boundaries are, I can now develop, right, robotic tracking strategies that allows me to essentially map out where these boundaries are. And so this is this idea of like, can I somehow, right, build a map of this environment? I can think about these coherent structures, right, as sort of highways, right, in the ocean. And then they can be super useful from a planning perspective, okay? But there are other types of structures. And there we go. Okay, so let me tell you some things that are going on here. I want you guys to, the boat is right here. They're trying to get from this starting location, which is the blue circle, and they're going to try and get to the green circle, okay? And now compare it to this one. And let me make sure that that plays. And so there's a difference, right? So this one gets caught within this eddy that is kind of shown here, highlighted by the pink region, whereas this one, it goes a lot slower, but actually what you'll see is actually it will go around and will make it to its goal, okay? And the difference, fundamental difference, is that this one is aware of the fact that I have this eddy region and that I am actually now leveraging the surrounding flow dynamics in order to help me to get where I want to go. And so it's this notion of coherent sets, okay? So if you look at the animation at the top, these are two sets. I have the black one and I have the yellow one. And they're going to get, I'm going to turn on my background flow, so time, right, progresses forward as you move from your left to your right, okay? And what you see is the fact that the collection of black particles stay together, whereas the collection of yellow particles kind of disperses, okay? And so this is what we call that the collection of black particles, right, they form this coherent set. So even though there's this background dynamics going on, there is still some sense of, right, sort of consistency that happens. And so they tend to stay together, okay? So, and now hopefully I've convinced you that, these are kind of important things, right, to know from a planning and controls perspective. I can then tell you how we can identify these coherent sets from data, okay? And we're going to do this using things called transfer operators, okay? So, I drink a lot of coffee, probably more than I should. So before we talk about transfer operators, let's kind of, let's do a mental experiment here. Okay, so I got my cup of coffee. I am going to pour some milk into my cup of coffee, and I'm going to stir the milk in with my spoon, okay? And so the question is, given a single milk particle, okay, can I predict where that milk particle ends up 1 minute after I've poured my milk in? And so this is what I do in my lecture. I'm like, how many say yes? And then, you guys will say yes, will raise your hands. How many say no? And then the ones that will say no will raise your hands. But the answer is, in general, no, you cannot tell, right? And that's fundamentally because the individual trajectories are mostly chaotic. And so it's really, really hard for you to predict where they are. However, if I ask you, what is the distribution of milk particles, right, 1 minute after you pour this in, right? Now, when I say, can you predict this? And then I ask the question, how many say yes? We should all raise our hand, right? And it's because, right, so after 1 minute, and I've stirred this with a spoon, right, it should be nearly uniform, right? The distribution should be nearly uniform. And so this is kind of the main insight about transfer operators, right? It's about, instead of predicting individual trajectories, which is hard, I'm actually going to predict, right, the action of dynamics on a collection of particles, or a collection of initial conditions, okay? And so for me to do this, right, I need to first talk about this thing called a transition density function, okay? And so here's the idea. Given some stochastic process, x, right, and some time interval, little tau, then I want to be able, so the transition density function tells me, right, what is the likelihood that that stochastic process is going to take on some value y after some time interval tau, okay? Now, from this transition density function, I can then talk about transfer operators, right? Because the transfer operators are now telling me about the evolution, right, of the densities over time, right? And there are a lot of different types of transfer operators out there. We are going to talk about Koopman today, and partly because Koopman, there's a connection between Koopman, right, and using data in order to estimate, right, these kinds of dynamics. And so the Koopman operator is an example, right, of this transfer operator. The way we think about Koopman, it's actually a push forward on functions of the state. So here, this is why it's not just script k times x, it's actually script k times, g of x, okay? And what this is telling me is, what is the likelihood, right, that the value of g of x is going to become y, right, over this future time interval tau, okay? Now, the way to think about these sort of functions, these g functions, is that if you think of them as lifting functions, right, this is very similar to those of you who are coming from a learning background, right, to this notion of lifting in kernel methods in machine learning, okay? And in fact, in 2020, people have shown, right, you can make this connection between the Koopman operator and do this using these reproducing kernel Hilbert spaces, okay? So here's kind of this idea. I'm going to start with my state space. I'm going to lift this up, right? And now within this lifted space, these are sort of conditional distributions, right, of the state. And then I'm going to then be able to, in this lifted space, come up with approximations of the Koopman operator using these covariance and cross covariance operators, okay? Now, I'm going to have a nicer picture so you can kind of, if this is a little hard to, but I'll show you in a picture in a little bit. But the key point here is as follows, is that we have a way to approximate this Koopman operator through data. And that's kind of the key part, okay? So this is another way to think about this. Here's my dynamical system, right? The dynamics are nonlinear. And I am now going to do this lifting, okay? So when I'm working here, right, this potentially is a finite dimensional space. But when I do that lifting, I'm actually going to be lifting this into functional space, and this is now infinite dimensional. The advantage of this is that I took what was fundamentally nonlinear, but then in this higher dimensional space, the dynamics have become linear, and it's that Koopman operator, okay? Oh, one thing I need to say, a lot of the early works on Koopman operator was actually done here at Princeton by Professor Clarence Rowley in collaboration with Igor Mesic. So I just wanted to mention that. And so in function, so keep in mind, the Koopman operator is an infinite dimensional operator. But the point here is that you can actually get finite dimensional approximations from data, okay? So if you have measurements of your system, then basically you would do this lifting. I'm purposely doing this in a slightly different way because, you know, the measurements are not always, right, sort of one-on-one related to your state space. But then you do this lifting, and then you lift this into a higher dimensional space. Now, we've seen this. You should have, for those of you who have seen versions of this before, here's kind of a way to sort of ground yourself. So if you use identity functions for your lifting, okay, then this is what we call dynamic mode decomposition. And again, Clarence actually and Igor did a lot of the earlier work on DMD. However, if you use a set of hand-picked dictionary functions, okay, to do the lifting, this is what is called extended dynamic mode decomposition. If you use a set of kernels to do the lifting, this is called kernel dynamic mode decomposition. And then these days, for people who are doing machine learning, right? So you even have Koopman autoencoders, and the idea here is you would try to sort of, you know, the composition of the lifting and the operator and the delifting, all of that sort of gets learned as a single autoencoder, okay? So the way we're going to do this is that we are going to assume, so we're going to think about this from a kernel perspective. Our kernels are going to be these random Fourier features, okay? And then we're going to sort of take that result, right, that tells us that we can do this finite dimensional approximation to the Koopman operator using those cross-correlation and correlation matrices, okay? And then we kind of optimize over the loss of the function. So in this particular case, we can, you know, think about this propagation error. So when you push things forward in time, you want to minimize, right, your prediction. And then here, this is when you're kind of doing your reconstruction. So you're kind of delifting, and you're bringing things back down to your finite dimensional space. So you want to sort of reduce that error. So here's kind of the thing to keep in mind, because in some of the Koopman literature, right, a lot of the challenge is finding these lifting functions that make sense for your specific problem. And so we kind of circumvent that because essentially we're saying, look, we can use these random Fourier features, right, as our lifting functions. We don't quite know the parameters, what those parameters value will be. But because we're kind of using those lifting functions in our reconstruction, right, we basically can solve, right, use the data to then figure out what the best fit for those parameters are, okay? So we're kind of simultaneously solving for the lifting functions as well as the operator. But the neat thing about Koopman is that the eigen components of Koopman actually gives you a lot of information about the dynamical system. So let me show you what I'm talking about. So here, the color signifies the initial x position of the particles, okay? And then we kind of just run the animations. And so eigen decomposition, so the eigenmodes of Koopman, they can be used to help you identify these things called metastable sets. And really, that's just a really fancy way of saying that helps you identify your coherent sets. Okay, and so what you're seeing here, this is like the dominant eigenmodes of the estimated Koopman operator. So for the Duffing oscillator, you do see, right, those two sinks. This double gyre, you see your two eddies, okay? And then for the Bickley jet, you see that primary sort of jet stream in the middle, and then, you know, your counter rotating vortices around it, okay? So this is pretty neat. We then said, well, since we can do this, now we can solve kind of the active learning problem, okay? And this is, you know, this is stuff that Professor Naomi Leonard's group have done, you know, for quite a many years, this notion of adaptive sampling, right? You have some data, you can use that data to create a model of this environment. You use that estimated model to figure out what next regions to go to so that you can collect more data, which then can be assimilated and then is used to help improve your model and so on and so forth, okay? So here's kind of this idea. I can take my vehicle, it will collect some data, and then we can use flow measurements, we can use the vehicle trajectory data. We then throw this into our sort of Koopman estimation framework, okay? And we're kind of, in this particular case, simplifying the objective function that we're optimizing things over. Now, the downside about Koopman is that I have no way, right, of understanding how good this model is, right? There's no sense of uncertainty. So what we do is we then ensemble the Koopman model that we have, and then we use the ensemble models to then come up with an estimate of regions of high model uncertainty versus regions of low model uncertainty, and then from there you can pick your next best locations, okay? Okay, so basically, here's kind of some results. These are the streamlines, okay? This is the Bickley jet, this is the streamline. These are basically pixel-wise errors, okay? So the darker green it is, the higher the error. The whiter it is, the better we're doing. And then again, sort of this is a lid-driven cavity flow. So this is just, think about having an obstacle, and then you have this larger flow, so you get these little eddies in those little corners, okay? We then compared our sort of method with my students spent a long time trying to get the best fit she could with a Gaussian process regression equivalent, okay? And so what you're seeing is like overall, we are doing better, right? The Koopman is doing better. But here's kind of the other thing. So the main line, so this is the active sampling problem where you kind of change your sampling locations, right? You move. But here's kind of the thing. The blue line, the solid blue line, that's our method, okay? The dotted lines are just different variations of a GP, okay? So you're using different kernels for your Gaussian process regression. And what you're seeing is the fact that, like, look, we actually are able, so this is mean error in terms of the magnitude of the velocity vectors. This is cosine similarity, so that measures how far apart direction-wise the individual vectors are. And so actually, the Koopman actually does quite well, okay? And the Koopman, so the nice thing about Koopman as well is that, with GPs, you eventually run into this problem of the fact that you have to invert this Hue matrix, and that becomes really costly. And so we don't have that kind of an issue with Koopman. So this is why we sort of, for these low sample scenarios, we pick GPs, because GPs are actually doable in these low sample regimes, and the fact that, we can show that we're doing better. Okay, so this is this idea of building, right, collecting data to build a better map of this environment. I never thought that I would ever give a talk on SLAM. That was just not what I do. And yet, I am going to be talking, at least for a little bit, on SLAM. So what about localization, right? So one of the most common techniques out there is this notion of factor graphs, right? So you can sort of, think about all your poses. You think about if you have known features in the environment, and then you can sort of, based on your measurements, you can then minimize, right, the errors and then fit everything into place, okay? So, so the standard SLAM in terms of factor graphs, what you're doing is you're saying, look, okay, this is my odometry errors. These are my sort of landmark, right, sort of position errors based on locations that I know of. And then I'm going to sort of minimize, I'm going to find the estimate, right, of my robot position that kind of minimizes this total sum of errors, right? And then once I've done that, I have a better estimate of my localization, then I can use that to improve my map, okay? So I can do this in a flow. I'm just going to have to change things up a little bit, okay? like I said, there's no features, right? So this is the part where having a team of robots really shine, especially if you can see each other. And so this is why, having more than one robot makes a lot of sense. We are then going to use a parametric representation of the map. So in the previous example with Koopman, right, this is this idea where I have this dictionary of I have my kernels. So it's kind of the same thing. I can sort of pick a dictionary of functions, and then I'm just going to optimize, right? I'm going to figure out, well, how do I weight each of these terms within my dictionary to come up with a representation of the map. And so I have a couple of new factors. So I now have this notion of a streamline. I'm in a flow. I'm going to assume that all the robots are being advected by the same background flow. So that gives me a streamline factor. And then if I sort of have the ability to do bearing and range estimates, right, between myself and other members in the team, I can also have those measurements. And then I could just throw everything into my optimization. So now I just have extra terms. So there's my stream factors. This is in case, so underwater vehicles, if you want to measure the flow velocity, they have this thing called an ADCP, which is a acoustic Doppler velocity profiler that actually allows you to measure the speed of the water, okay? So if you have those measurements, you can add them to this. In the original form of the work, we assumed that the robots were just kind of passively drifting. ADCP sensors are expensive and they're heavy. And so, having these measurements may not be super realistic depending on what you're trying to do. And then the last component here is that, we kind of pick, right, we want to optimize over the parameters, right, of my parametric map. But I'm going to do this over norm 1 so that I can promote sparsity. So those of you who are familiar with SINDI, so this is sparse identification, right? So we actually use SINDI sometimes. Other times, we do our own thing, basically. But this is the nice thing about this approach is it's actually really, really flexible. Let me just show you a bit of a result. So this is sort of the error, again, high meaning, so red meaning high error in terms of differences in vector directions. This is kind of differences in what your estimated, so the dead reckoning is the one that you haven't corrected for your errors. And then the blue one is the one that you've actually, right, so this is your localization estimated trajectory. And so the nice thing is you can see that they actually line up with the black, which is ground truth. Sometimes it's hard to see. And then you see that the growth of the errors, right, is somewhat contained when you have the ability to do this, okay? One more thing that I wanted to say, in this case, in the top case, the library of functions, we just use those random Fourier features. They work really nicely, especially with this double gyre system. In the Gulf of Mexico, so this is actual ocean data. And so normally what happens is it's really hard to figure out what exactly the right sort of kernels or library of functions are supposed to be. So what we did is we just said, look, let's collect this data. Let's do a DMD decomposition. So effectively this is, think about, you're taking the data and you're saying what is the equivalent of a principal component analysis on the data. So what is the lower dimensional manifold that the dynamics live on? And then you use the DMD, the dominant DMD modes as your elements in your library, and then you can do the same thing. So in that sense, it's kind of actually really general, which is really cool. Okay, so I'm going to take a slight segue, because I'm a roboticist, and I haven't shown you enough videos, and so I'm going to have to show you some cool videos, okay? Okay, so another way to think about embedding structure, right? So how do we leverage what we know of physics and the data that we can collect? So this notion of knowledge embedding into your learning, okay? And so here's kind of this idea. Most of the time, given whatever system that I'm interested in, I have some notion of a model, okay? But there are going to be some complexities, right, that I may not fully understand, or that it's just really hard for me to model. Okay, so in the case of a quadrotor, the local aerodynamics can be pretty complex, especially when you're flying in high speeds, right? And so I'm going to pose this learning problem as a residual sort of physics, right? I'm going to learn the residual physics. And the way I'm going to do this, I'm going to sort of represent the residual physics using a neural network. And I'm going to be somewhat picky about what kind of, right, I'm going to use a neuro ODE. Part of the reason I want to do a neuro ODE because it fits really nicely with my regular ODEs. And so here's kind of the idea. I have these measurements, right, and these are generated by some sort of linear, or it's not linear, it's an ordinary differential equation. And I'm going to come up with an estimate, right, of basically the differential equation, but I'm going to do this in a way that it becomes this, this neural network, okay? And so the way I'm going to, right, so I'm going to sort of, my loss function is, I'm going to take, right, my forward, right, estimates of where the system is going to be some time step in the future, okay? And if I do, so this is posed as a sort of, you're minimizing your cost functional, because this is kind of now a function of functions, right? And what's really cool is that, right, now I just have these, theta is now your parameters of your neural network. And so I have a way to kind of do this. This is the optimization problem. I'm going to find the set of thetas that minimize the error between what the neural network output is in terms of the velocities, right? And in this case, again, I have measurements of position. Okay. Let me skip this, but the idea here is that here's my cost function. I'm going to, this is how you translate all of these things, right? So I have my sample trajectories. And then basically the idea here is at every step you're just trying to turn those little red segments that are being predicted by that neural network, and you're going to, and your physics, and you're going to squash it down, right? So that you get the red segments to line up with the blue segments as much as you can, okay? Okay, so here's kind of this idea. I can do this, okay? And it comes out really nicely. And now I have a really nice high quality description of the dynamics of my system. It's just a model, so I could just wrap a controller around it, right? So I'm just going to wrap an MPC controller, so that's your MPC. Now, the blue part, that's the K-node model, right? So this is the physics plus data model. I can do something even better. I can think about, so one thing to note, this is actually from Nora Ayanyan's group at Brown. So these are PIV measurements of the amount, the velocities of the air, right, that comes down from two quads flying on top of each other, okay? So this is velocity, the red is high magnitude, okay? And the bottom figure, this is showing the amount of fluctuation. So this is the time-varying nature of those velocities, okay? This is a very hard thing to do because trying to model this is really hard. This is a very complex fluid structure interaction problem. Okay, hold on. But we can do that within this learning framework, right? So here's my two quadrotors without that nice high fidelity model. So here I'm going to be a little bit honest. I'm going to have to be honest because we did add a rough model for that, the forces that the top quad is exerting, but it's actually a really rough model. It was nowhere close to the actual data because we didn't know about the data until we finished the work. But here's kind of this neat thing. The closest we can get them is about within almost a single body length, right? So that's pretty neat. Okay, so we're like, this is pretty cool. But here's another thing that you can do. Again, it's just a model. Here's my MPC, okay? So now the quad is just being told, just fly in a circle at a fixed height. And then my graduate student, Konyao, is just coming in. He's just adding little washers, extra washers on this. And so over time, right, the quad is going to lose altitude. And so because you didn't account for this extra mass, right? But when you wrap this L1 controller around it, and so the L1 is kind of your adaptation. So we know, right, that your learned models don't always perform well, right, when you subject them to to disturbances that are out of distribution. So this is an example of an out of distribution disturbance, right? But that is essentially what the L1 is compensating for. So we can handle all the within distribution because we have this nice learned model. But now, just with the simple, this is, okay, I met the inventor of L1 a couple, early in September during an NSFPI meeting. It was amazing. But it is a pretty old technique, right? This is something that has existed for quite a while now. Okay, so this is neat. So let's take a look at this. So we can fly 2, so let's fly 3. Okay? So here's a really cool thing about this video. The bottom quad and the middle quad, we did not retrain them. We just took the original trained system when we just had the 2 quads, and then we applied it here with the 3 quads. What we did do is we added an L1 adaptive controller on them, okay? And so this is why you're kind of seeing this is like the best result, okay? Nevertheless, this is a super interesting interaction problem, because we had assumed that the quad that was going to was going to be subject to the most force was going to be the bottom quad. And instead, we did not account for the effect of the bottom quad on that middle quad. And so it seems, right, that actually it's the middle quad that is experiencing the most complex aerodynamic interaction, okay? So that's pretty neat. And this is the even cooler part. I always have to show this. Okay, so here's what we did. L1 with nominal MPC, no learning. This is MPC, but with that really rough model for the downwash force, okay? L1 added on top of this model with just that downwash force. K-node with, right, sort of your learned model. And now you add your L1. This is not wrong. You do really well with just L1. And L1 is cheap. No training data, no learning. This is all just hardware, you're done. Okay? And this is kind of, this is a really important lesson, right? In the sense that, like, obviously, you do better when you combine some of these traditional things, right, with the modern learning approaches. But this is expensive, and when you're cost limited, guess what? Some of these old-fashioned things that, I grew up on, that I do, actually work really well. And so this is kind of the really interesting result. Okay. So let me just conclude, right? So I've focused mostly in the ocean, but a lot of these things apply in all kinds of environments, right? They present really interesting challenges, but they also offer a lot of opportunities. The fact that the vehicle and the environmental dynamics are coupled makes planning control really hard. But if we have this ability to build better models, then we have this ability to tap in, right? This is almost this infinite reservoir, right, of forces that we can use to help us move through the environment, okay? And of course, we need to be able to do perception, right? A lot of these ocean models these days are still really, really coarse, okay? And the other thing is, most of the times your robots are like, a meter, maybe less, most likely less. And what is going on locally, that becomes really important. And I know that people like Amy here, does really cool stuff. And then Radhika has, a lot of these cool new platforms. And then we're not even going into the communication, the challenges of some of these environments, right? But the idea here is that, if we can do a better job, right, of building sort of these systems, we now have this ability to deploy them and have them be able to sort of, collect this data. So these smart networks that I like to call them. And you can see how this is super useful in a city when you're interested in monitoring your drinking water quality, your air quality, right? Urban heat islands, these are all things that are becoming even more important, okay? But of course, these are these kinds of problems, data is expensive in the sense that they're just hard to come by, right? And so we want to be able to think about how do you do this, right, with limited resources, potentially with severe communication constraints. And so a lot of the strategies we want, right, is really about trying to make the most of what we have. And this is where, you leveraging on however many thousands of years of physics we have, sort of developed over this time. Don't throw that out, right? This is the stuff that we can really use that to help us do better. Okay, so I'm going to end. These are just my quadrators. We have the leftover window from whatever other papers, so we can fly our 2 quads through the window. Is that not playing? It's not playing. I got to make sure I play this. So anyway, thank you so much. It's great. It's always great to be at Princeton and being able to spend time with friends and make new friends. Thank you.
Wonderful. Thanks a lot, Amy. We have time for a few questions. So if you put your hand up, I'll run around with the mic. All right, great. Let's leave this here.
Oh yeah, I really like the use of latent dynamics for the ocean problem, and I was wondering, because I've seen similar things like embed to control, which was kind of an old paper that sent things to a latent space using neural networks, and then had linear dynamics that neural networks learned, but that didn't use anything like Koopman operators. I was just wondering what you see as the advantage. I guess I'm assuming by incorporating physics, you allow to have less data and less training time.
We do have a lot less data, and especially with these, we are only using a couple of seconds of training data, right? And then our neural networks are super shallow, so that just makes it. First of all, when you're ready to port this onto an actual platform, right? You don't have to worry about compute as much, so that's number one. But the main issue is the training data, right? What you're seeing with Koopman is that Koopman actually doesn't need a lot of training data. And in some, if you're saying I want to find all the coherent sets within this flow field, then yes, I do have to compute the whole thing, right? But I do, so this is the part where I think is really the important aspect of it. Training takes a lot of energy, and I don't just mean in terms of the amount of energy produced to power the computers, right? It is about all the time that you guys are spending in the lab, running the experiments. How many times do your experiments not work, right? And then you have to rerun them and all of those things. And so that's it's costly. Out in the field, right, when you have to then take your sensors and actually harden them for actual long-term operations, that's another added cost. And so these are all challenges, right, in terms of getting large amounts of training data.
Cool, thank you.
I enjoys this talk so much. I had a question about how you were estimating flow fields. It was a little bit earlier in the talk, but the Gulf of Mexico, for example. Is it just satellite data that is being used? Or maybe I can ask the question slightly differently. If I was put in a situation where I didn't know what the flow fields were and I wanted to actually build a map, what would be some of the options I would have to do that?
Yeah, so that's a great question. So you do need to, so first of all, it depends on the platform, right? So you can put drifters, and that's kind of the most common thing. You collect trajectory data, and then you take the trajectory data, and obviously the more spatially dispersed they are, the better you'll get. And then you try to fit a model. And so you can try to do something like Cindy. You can try doing something like Koopman. You can do, so there's a lot of different options on how you want to do that. Existing ocean models, right? These are basically large-scale, like direct numerical computation, right? The direct numerical models. They're solving full-blown Navier-Stokes equations, right?
About the Gulf of Mexico.
Yeah, basically. So they're big models, right? And so it's a combination of satellite data. They have buoys, right? Sensor buoys, and so they do use the data to constrain those models, right? But they're very high dimensional. And this is also part of the reason why they are so coarse, right? These days with compute technology, you can just increase the grid, sort of make that grid much, much finer, but that doesn't necessarily mean you have this more data to constrain it, right? And so there's gonna be kind of challenges. What is the really cool development is that one of my colleagues at Penn, so Paris Perdicaris, so he spent a year on sabbatical at Microsoft Research, and they now have this foundational model that can, basically it's like it's a transformer-based type approach. And so, but they're doing things in the atmosphere, okay? We have a lot more atmospheric data than we do, right, sort of ocean data. And so, but they are showing some really cool results because they can say, look, I can take this thing that was trained based on sort of wind patterns, but now I can actually use that to predict the spread of smog in a given city, right? So there's some nice ability to generalize in that case. But fundamentally, it's a question of data.
Maybe, can I just add one piece?
Yeah.
When you're doing experiments in your water tank where you had the example of your boat moving in it, are you already just knowing what you put in, or do you actually put drifters in that and estimate?
Yeah, so we do that, right? I have been trying to find someone who's willing to build me a nice, proper CFD model of my tank. It's very hard to convince a roboticist that this is really what is worth their time. So we don't have very good ground truth for our tank, and I think the tank is just big enough that even the HVAC system throws things off. Right, and so, which is the same case as my suspicion is, which is the same case for your tank, is that it's just large enough that there's going to be enough things that you can control for. Yeah.
Thanks for the wonderful talk. So I have a question that's probably going to show how little I know about oceans, but how fast do these systems change? Is there a risk that by the time you've collected your data and fit your model, the system's already slightly different than
that's
when you
a great
collected your
question. In some ways, we know and we don't know. And part of this is because, so all the models are what they call mesoscale models. And so this is the stuff that happens in terms of, months, years, right? And our sensing is really not great. So I think the highest resolution sensing, unless you throw drifter, or if you throw a glider into the ocean, these kind of existing sort of sensing technologies, the highest resolutions are these radial, they're high frequency radar, and they're kind of radial, and they're about 2 kilometers apart, okay? So that's kind of your spatial resolution. So oceanographers, at least in the last 5 years, have really now started, maybe even 10, really focusing on the sub-mesoscale. But they define the sub-mesoscale as things that happen from a couple of days, like a day to a week, to things that are less than a kilometer, right? And now that's great because that means they're really pushing, trying to get more data. But a kilometer is still a really long distance for a robot. And so that's kind of right, the scale. So in some ways, like we do know because there's enough kind of smaller, I mean, Amy probably will know a lot better because you can do things in the lab, right? That sort of, you can sort of, do these these dimensionless equivalents, right? But how do we then, what does that mean when you're out in the wild? As a roboticist, you're just a little hesitant to sort of fully trust that.
We may have time. I think this might have to be the last question before lunch.
Hey, great talk. I liked
Thank
it a lot. I had this is like a little orthogonal to the other questions so far, but I guess it's like to do with the like physics informed neural network type stuff, and like I definitely agree it'd be great. I would like to be able to reuse a lot of the physics we already see in the world. I guess a question I have for you is some of my friends who have worked on this in the past have told me like they can be really sensitive, very difficult to train. Like even if they can be more, sample efficient, it ends up being really hard to get to like something that works at the end, to the point of like then you start to like wonder like what is the trade-off? Is the pure data-driven approach just better purely because it's easier to learn or something like that? And I guess what's your perspective of like how do we bridge that gap and like make that work better? I guess.
Oh. I wish I had the answer to that. That's like the million-dollar question. So I do think, like the prevalence of these sort of, purely data-driven techniques, right, is because you have a lot of code that you can download, right? In scenarios where there's a lot of training data, it's easy to get good results, right? And my suspicion is that, companies are really interested in this because they have a lot of data, right? And they're trying to figure out what to do with all of this data that they have. I don't think you are, because of the fact that they're not really interpretable, right? How do you use this to like discover new physics, right? Mm-hmm. I don't think I have seen anyone that has provided a really straightforward, I understand that there's a possibility. I would be really interested in sort of being able to know how to do that. I think there's a lot of very interesting problems out there that if we had a way to figure out, what part of the stuff that we already understand is not, and sort of shed more light on the stuff that we don't understand. But, sometimes this is this thing about physics takes time, right? Like a lot of these, if you want a good foundation, you got to eat your broccoli. And sometimes you can't avoid eating your broccoli.
Cool, makes sense.
All right, wonderful. Let's thank Annie once again
Thank you.
for this wonderful talk.